Today we will be discussing the Huffman codes. We already have seen that in digital communication system, source encoding is very important. It is the first part of the digital communication system. Source encoder converts the digital input signal into another digital signal. It is required because the original signal may have redundancy. Hence, to reduce or eliminate the redundancy and ensuring the efficient representation of the source signal, source encoder encoding is very important. Huffman code is one of the source code which is of variable length, and it is also said to be the optimum source code. The approach here is, it is known as variable length encoding of symbol. Actually, it means the symbols will not be encoded with the same number of bits. It depends on the statistical information of the symbol. That means if a symbol occurs more frequently, the code associated with that will be of lower length, and hence this is efficient when symbol probabilities vary widely. So principle here is, use fewer bits to represent frequent symbols and use more bits to represent infrequent symbols. You can refer this figure and understand how it is advantageous. See, if we allocate the same space to all the symbols of the message, then let us say this is the actual space required to represent a message. Whereas if you allocate variable length to every symbol, in short, if we associate less space to a frequently occurring symbol and more space to the less occurring symbol, then there will be overall reduction in the total space required by the message. We should say this is nothing but we can use the bandwidth available quite efficiently. Let us understand this by one example. Let us assume that a given message signal is having the four symbols A, B, C, D, and these are the frequencies of occurrences of these four symbols. Rather, we can say these are the probability of occurring these symbols, frequency of occurrence of these symbols. So if we associate the equal length code to all the symbols, then we need at least 2 bits to represent every symbol, and maybe this will be their representation. This is the original encoding. Now what will be the encoding we may get with the Huffman code is this way. Means here you will observe that the most frequently occurring symbol is C. So in Huffman coding, only 1 bit is allocated to this symbol C, or rather I say symbol C will be encoded with a single bit. Then symbol B is encoded with 2 bits, where again the probability of occurrence is better as compared to the remaining 2 symbols, and A and D are having the least probability of occurrence, and hence the maximum number of bits are allocated to symbols A and D, that is 3 bits. Thus we can calculate here the requirement of the size of the message. If the original encoding is used, then we will be requiring 2 bits per symbol, whereas by Huffman coding it is reduced to 1.75 bits per symbol. So without loss of information, Huffman code always saves the space, and hence it is more efficient. Let us understand how a Huffman code is obtained. So here we have to consider, or rather form a binary tree which represents the Huffman code. In this binary tree, the edges represents the code. The code will be in terms of either 0 or 1, that is the binary symbols are used. The leaf of the tree represents the symbol. Path to leaf is actually gives us the encoding. For example, if we consider these 4 symbols A, B, C, D, then maybe we are getting this encoding for these 4 symbols. Like A is represented as 110, B by 10, C by 0 and D by 111. Let us have an overview of the algorithm to get the Huffman code. For encoding, initially we should know the frequency of the symbols in file. That means we will know the probability of occurrence of these symbols. Knowing this, we can create a binary tree representing the best encoding. Then use this binary tree to encode the compressed file. For each symbol, output path from root to leaf. So this will give you the encoding. And the size of encoding will be equal to the length of path. Thus we will have this binary tree that will be used for encoding the symbols. Now how to create a tree? This is the algorithm for creating the tree. Initially, we have to place each symbol in the leaf. The weight of the leaf will be equal to the symbol frequency. Then select 2 trees L and R, let us say. Of course, these are going to be the leaves initially. And then we have to select these 2 leaves in such a way that they will be having lowest frequencies. Then create a new node. The new node can be created by adding the frequencies of these 2 leaves L and R. So new frequency will be equal to frequency of L plus frequency of R. And this process is to be repeated unless all the nodes are merged into one tree. Let us take example to understand this algorithm or to follow the algorithm. Let us assume that we have these 5 symbols in the message and these values in the circle. Let us consider them as leaf of the tree. They represent their frequencies of occurrence. So as a first step, we have to select the 2 leaves having the lowest frequencies. So you can see here A and H, these are the 2 leaves having the lowest frequencies, that is 3 and 2 respectively. So these 2 leaves are merged into a new node, and this new node now will have the frequency which is sum of the frequency of A and H, that is equal to 5. Now next we can consider the new leaf here, and here we find that the leaf C having the same frequency as this new node. So let us again merge them to get a new node having the value of summation of frequencies of nodes leaf C and the new node. So that is the frequency 10. So this new node now have the frequency of 10. Now remaining are the 2 leaves. They can be also parallelly merged into a new node. So this new node will have now frequency equal to 8 plus 7, that is 15, and then this complete tree can be formed like this, and it can be joined with the arrows. So at the root we will have a node with frequency 25, that is generated by merging the lowest frequency nodes, and then if we consider this as a root, and as you go from this root to the leaf, you will get the code for that particular symbol. Here the codes are been written. For example, for symbol E, we have to follow from the root, that is this point. Next is to node 15. So this is the code associated 0, and from 15 to reach to E, we have to follow this particular branch with code 1, and that's why E is having the code now as 0, 1. In the same manner, to find the coding for symbol I, we follow the path from 25, 15 to I. Thus 0, 0 is the code for I. Then if you consider symbol C, then from this root node we have to follow this direction from 25, 10, 5. So it is 1, 0. So C will be coded with a code as 1, 0. To get the code for A, we follow this path again, 1, 1 and 1. So here you see code for A is 1, 1, 1. And lastly for H, we again follow this path. So 1, 1 and H. Thus we get a Huffman code for each symbol, which has been displayed over here. Now assume that the input is ACE. So what will be the output of the source code to code these three symbols? The output will be, first the code for A is 111, followed by code for C 10, followed by code for E, that is 01. So the output is going to be 11110001. Now this is supposed to be decoded. We should be able to get the original message at the receiver. So we have to read this compressed file and binary tree, and we use again the same binary tree to decode the file. So here we have to follow path from root to leaf. Just look at this. We are here at the root. The first symbol is 1. So from this root node we follow this path 1. Next is again 1. So we continue on the same line and till we reach up to a certain symbol. The next bit is again 1. So we reach at the symbol A. So we can immediately decode this group of bits 111 as symbol A. Then next is 1. So again we had to go to root and follow the new path. New symbol is to be retrieved. So we are following this line and reaching here at the new node, that is not corresponding symbol. So we continue further. So next bit is 0. So we have to follow this path shown by the red arrow, and then we reach to symbol C. So next message is symbol C. Again we come to the root to decode the next bit. So next bit is 0. So we have to follow this path. We are still not at any leaf, so we continue. The next symbol is 1. So when we follow this path we reach to symbol E. Thus the code is complete and we finally get the decoding as ACE. So this is how we can code and decode using the Huffman coding techniques. So let us now discuss what are the important properties of Huffman code and why it is so important. This Huffman code is known to be a prefix code. That means there is no code is a prefix of another code. The coding can be stopped as soon as the complete code is found, and there is no need for end of code marker. Another property is it is non-deterministic. That means multiple Huffman coding is possible for the same input. Imagine that there are two trees with the same minimal weight. So in that case you may land up with the more than one solution for the Huffman coding. It is a greedy algorithm too, that is it chooses the best local solution in each step, and it combines two trees with the lowest frequency. Still this yields overall best solution, so that's why we call it is a optimal prefix code, and it is based on the statistical frequency. Of course this is not the best code. You may find better comparison with another code also depending on the data. For example, pattern dictionary is one of the way. Of course that is not part of our today's discussion. So finally, we conclude that Huffman code that way is one of the optimal code for source coding, and we have also studied how we can encode and decode using Huffman codes. So thank you very much.